Good evening viewers, this is InfoBurst. A very warm welcome back. We are going to discuss today mysteries beneath the ice, the secrets of Antarctica. Antarctica's Thwaites Glacier, spanning an area nearly the size of New Mexico, holds a significant potential to increase global sea levels by a meter if it releases its ice. This unstable giant acts like a plug for much of West Antarctica. Scientists predict that if Thwaites collapses in the upcoming decades, it could release enough ice from neighboring glaciers to increase sea levels by an additional 3 meters. To understanding the dynamics at Thwaites Glacier and other glaciers across Antarctica is vital yet extremely challenging. Researchers worldwide have spent decades gathering data and perfecting the science to determine how these glaciers operate and their potential impact on the planet as the climate changes. Viewers, one institution at the forefront of overcoming these scientific challenges is the University of Texas Institute of Geophysics. Scientists at UTIG have been investigating Antarctica's ice for nearly 30 years, leading the way in geological research. In 2016, UTIG joined the Korea Polar Research Institute's effort to monitor Thwaites. By 2018, the US and UK National Research Foundations announced $50 million in funding for an international collaboration focusing on the Thwaites Glacier system, with significant contribution from UTIG as well. Viewers, the glacier models used by this collaboration rely heavily on aerogeophysical data collected by UTIG in 2004. UTIG senior research scientist Don Blankenship led the challenging 2004 January, teaming up with the British Antarctic Survey and glaciologist David Moon. Their primary concern was the lack of knowledge about the West Antarctica region despite its potential for collapse. In the late 1980s, Blankenship and other glaciologists had already determined the crucial role of the underlying geology in a glacier's behavior. They pioneered detailed analysis of ice sheets, subglacial geology. Viewers, revealing added sea level threats from Antarctica. For example, Blankenship's team discovered that glaciers often rest on a bed of meltwater, which hastens their movement like a water slide speeds swimmers into a pool. However, for many polar glaciers, the scenario is more complex. During studies in the late 80s, Blankenship's team found that beneath the glaciers feeding into West Antarctica's Ross ice shelf, where there was mud instead of water. This mud, glacial till, was sedimentary leftovers of rocks pulverized by ancient glaciers. The mud infused with subglacial water allowed these ice streams to move dynamically, initially held back by the mud but changing over time. These findings have significantly influenced UTIG's glaciology studies. The UTIG team has broadened its focus beyond West Antarctica. By the 2000s, they ventured to the west southern reaches of East Antarctica, developing the ICE CAP International collaborative exploration of the cryosphere through Aerogeophysical program. Satellite monitoring revealed that areas like Totten Glacier while losing ice and mass. Whereas field research showed that parts of East Antarctica included unstable reservoirs of ice held within rock basins below sea levels, making them susceptible to ocean erosion. Blankenship and his colleagues developed a high-resolution map of the Aurora subglacial basin structure, revealing that about one-fifth of the basin extended more than 1 kilometer below sea level. This made it vulnerable to destabilization by the Southern Ocean, with the potential to raise sea levels by at least 3.5 meters. The team also discovered signs of past instability, indicating that the ice sheet had advanced and retreated multiple times, eroding a large system of fjords into the subglacial topography. Whereas further investigations focused on Totten Glacier, the main ice outlet of Aurora subglacial basin. The team used airborne gravity measurements to map the seafloor beneath Totten, revealing two unexpected seafloor Thwaites troughs that could allow warm water to reach the glacier's grounding line. This deep warm water, originating from other oceans, could enhance ice melt along Totten Glacier's grounding line. Whereas the researchers also explored the impact of wind conditions on the glacier's melting. They found that the winds over the Sabrina coast, influenced by global atmospheric changes, stirred up enough deep water to breach the ridge at the edge of Antarctica's continental shelf. This allowed warm water to reach Totten Glacier's cavity, contributing to its melting. Recent studies by UTIG researchers have shown that wherever an ice shelf was eroded from below by warm ocean water, matching grooves formed on the surface. Warmer Antarctic air temperatures have added meltwater into these grooves, causing surface-driven melting. The separation of a large iceberg from the main ice sheet was associated with this process, and many other glacier systems have the potential for similar events as air temperatures continue to rise. At last, thank you viewers for joining us on this journey through the fascinating and critical research happening in Antarctica. The work of scientists at UTIG and other institutions help us understand the potential impacts of glacier movements on global sea levels. Stay tuned to InfoBurst for more exciting and informative content on the world's most pressing scientific discoveries. Don't forget to like, subscribe, and hit the notification bell so you never miss an update. Until the next time, keep exploring and stay curious with InfoBurst.